Hi everyone, this is Shadi Alparkuni, a young investigator group leader at Helmholtz AI, Helmholtz Center Munich in Germany. It's my pleasure today being here at your workshop, at your CVPL workshop of medical computer vision and talking about deep federated learning in healthcare. So my agenda for today, I'll give brief introduction about federated learning and its importance in transforming clinical workflow. Before presenting two recent works, first on how we could train federated models without annotations for brain pathology segmentation, and the second one on how we could leverage unlabeled data for skin lesion classification, which has been recently accepted at the MICAI. Then I'll finish with concluding remarks and some activities that I have been involved in recently. So the first question that we probably need to address before talking about federated learning, whether we need to empower the clinical workflow with the machine learning tools. So to address this, let's have a quick look on the clinical workflow and the common challenges over there. So one of the major challenges is indeed the staff shortage. And this is what has been reported in one of the recent reports by the Royal College of Radiologists, where they stated that 75% of the clinical directors of the UK Radiology Department feel there are insufficient clinical radiologists to deliver a safe and effective level of patient care. This might be slightly better here in Germany. Nevertheless, the heavy workload in terms of anomaly detection, manual segmentation, qualitative measure, staging is yet another challenge. Both challenges have led to error and discrepancies with an estimated day-to-day error rate of 3 to 5% in radiology practice. And what makes things even complicated is the high inter and intra-observer variability. So to this end, we identified three potential areas where AI can mitigate these challenges: data curation, computational algorithms, and quality assurance. And this is what shaped our research portfolio in the last few years. Tackling the major challenge, technical challenge of data scarcity, domain shift, generalization, data heterogeneity, working with multimodal data, and finally, robustness and explainability. However, what I realized that the key to the real transformation to the clinical workflow is indeed investigating the long tail data distribution. In other words, while we build models, machine learning models that exploit the contributions that we made to tackle these technical challenges, we need to explore the long tail data distributed in different hospitals and institutes. And of course, in a privacy preserved way to utilize such collective intelligence. And this is what I'll be talking about in the next few slides and try to convince you that the federated learning is the key here. So first, it has a philosophical perspective. And this is where James Sowisky made the case in his book, The Wisdom of Crowds, that large group of people, crowds, are smarter than individual, no matter how brilliant they are. And he brought a couple of examples showing that the crowds are better at solving problems, innovating, reaching wise decision, and probably predicting the future. However, he set a few conditions to utilize such collective intelligence: diversity, independence, decentralization, and coordination and aggregation. The second point is more technical, and this is what Sun et al. Have investigated the question of what happens if we increase the databases by 10x or 30x, yeah? And in particular, if the annotations come even from noisy labels. And their findings were quite surprising. It turned out the collection of larger scale database helps in representation learning and logarithmically improve the performance no matter the initialization or fine-tuning used. And no matter how noisy the labels are, indeed. So having access to this large-scale database is the key to improve the performance. However, it's not straightforward. In particular, in healthcare, where data sharing is not systematic, since collecting, curating, and maintaining high-quality databases takes a lot of time, considerable time, efforts, and expense. Besides, privacy concerns have been triggered after a couple of works showing that even anonymized brain MR data can be identified if we have access to facial recognition databases. This is where a lot of regulations came recently, like HIPAA and GDPR, to suggesting that federated learning could mitigate these challenges. So how federated learning works? So basically, it's the process of training an objective function, say segmentation or predictive model, where the data is distributed to different hospitals or institutes. And it turned out solving this objective function can be done with the fit average by McMahon et al., where you simply share the initialized model parameter or the initial global model parameter to the clients, to the hospitals trained locally on their own data. Then they share only the parameters, the updated parameters to the global model, where they get averaged or weighted average to update the model parameters. And you keep iterate this process until convergence. Two key differences to the distributed learning though. First, it's communication efficient because you don't need to pass the model parameters to all the clients. However, you can just simply pick a few clients. Second, the data are not identically distributed. This is quite different from the distributed learning where the data all centrally, then you distribute it to the clients. Here, every single clients, they own their data and the data are not shared at all with other clients, neither with other clients nor with the global model. And that's why you might have a discrepancy or a domain shift between the data here. And this is what the so-called here non-IID, non-identically independent distributed data. And this is indeed one of the major challenges in federated learning. And this is what Zhao et al. Here showed that the accuracy of federated learning models might drop drastically by up to 50% for networks trained on highly skewed non-IID. So it's really a severe problem for the federated learning. And of course, there are many solutions have been proposed since then, tackling this problem by either adding a regularization term to the fit average algorithm or introducing momentum to keep the previous gradients or previous updates when we update the global model parameters, or by simply weighting the objective function with the class distribution to mitigate this non-ID challenge. Other methods try to tackle the problem from different point of view by either sharing a global data to all the clients or by modeling the data statistics, which is reflected in the patch normalization stats and parameters, and by either keeping or sharing this information with other clients. While most of these works try to mitigate the non-ID problem, real-world data might have more challenging non-ID scenarios, including domain shift, noisy labels, and poor quality data. So in the next slides, I'll be presenting our recent work on brain pathology segmentation with the help of disentangled representation. So the question that we were investigating, whether bringing more data in a decentralized fashion coming from different clients and hospitals would improve the anomaly detection and pathology segmentation in brain MR imaging. So we based our work on the previous efforts that have been published in MID-IA and RSNA, where a convolutional autoencoder was used to train healthy brain MR data and then used to reconstruct a pathology input and try to compute the residual between a pathology input data and the pseudo-healthy version of it. And this is indeed what you see here, these residual for different pathology like multiple sclerosis and glioblastoma. And what you could see here that the pathologies are highly overlapped with the ground truth annotations that came from the physicians. One of the key findings of this work is the fact that the performance of our anomaly detection is not only significantly better than simple thresholding, which is used in clinical practice, but also compatible to the supervised unit model, as you can see here. And this low performance of the supervised unit is due to the poor generalization to other data set, which can be attributed to the domain shift between the different databases. And indeed, this is what has been also reported in the literature. So one of the key findings of this work, that the MS lesion volume and also other like brain tissue volumes and cortical thickness measures might be largely dependent on the scanners and scanning protocol, as reflected here in this figure. So this is the same lesion, the same brain, but the lesion size just, differ from one scanner to another. So this motivated us to design a novel method that based on the assumption that anatomical structure information, like the brain shape, is somehow shared among the clients. So we're going to see the same shape among all these clients or hospitals. Whereas the appearance, like how they look like in terms of intensity profile, etc., is somehow, due to the scanner or imaging protocol, is somehow different. So we try to disentangle the feature representation into two. One, capture the appearance, and another one, capture the shape. And we share only the shape parameter with other clients in the federated setting, while we keep the shape or appearance representation private and stored locally in the client or the hospital. To enforce this disentanglement, we introduce two objective functions. First, the shape consistency loss, which try to minimize the distance between the shape representation of a given image and its slightly augmented version with the gamma shift to enforce this consistency here. The second loss is the latent orthogonal loss, which try to enforce the orthogonality between the appearance representation and the shape representation and make them more independent to each other. So we train our method on around 1,000 scans from multiple sites with real data and tested on around 200 scans of MS lesions and glioblastoma, coming also from a couple of publicly and in-house databases. So what you can observe during the training, that our model learns a shape embedding that is orthogonal to the appearance and consistent under different intensity augmentation, as you can see here. Also, all shape representation of healthy brains are grouped in one cluster following our hypothesis, whereas the appearance representation were individually clustered and far away from the shape cluster, as you can see here. This was also reflected in the quantitative results. For example, what you see here is the dice coefficient of the autoencoders trained locally on the within the hospitals, and on a data lake where we bring all these databases in a central place and train an autoencoder on it. And what you could observe here, that the data centralized one is indeed outperforming all these data clients in the reconstruction, and this is reflected in the reconstruction fidelity, the structure similarity index, and also was able to detect the anomalies and segment them better than the local models, and that was reflected in the dice coefficient. Most of the state-of-the-art federated learning algorithms were also outperforming local models with a big margin. However, it's obvious that our model, with the power of disentangled representation, was able to mitigate the non-ID challenge and was superior to other federated learning algorithms. Here are some quantitative examples where you can see how our model was able to detect lesions better than local, data centralized, and also fit average algorithm. This also holds for challenging cases. To measure how good we are with respect to the lesion size, we plot this figure where most of the models performing quite well on big lesions. However, they just simply failed on clinically insignificant one, suggesting that a lot of work is required to improve the detection of small lesions. So far, we presented work how we could utilize this knowledge or this long tail distributed in different clients in unsupervised fashion with zero annotation to do brain pathology segmentation. What I'll be presenting next is how we could leverage unlabeled data with a small portion of annotated data in a semi-supervised fashion for skin lesion classification. And of course, one could think about semi-supervised learning as the straightforward solution. And the way this could happen, that you do, again, the fit average algorithm. However, now your objective function is not only supervised, however, it has two parts. First, you want to minimize the cross entropy between the labeled data, the label, and the prediction of weakly augmented version of your input data. The second part is called the consistency rigorization term, where you try to minimize the cross entropy between a pseudo label, which is generated by passing unlabeled data to a weakly augmenter, pass it to the model, which has been trained in a supervised fashion. Then you get the prediction, then threshold it to get the pseudo label. And this is how the pseudo label generation works. And you try to minimize the cross entropy between the pseudo label and the prediction of a strongly augmented version of this unlabeled data, as you can see here. Minimizing this objective function enforce some sort of consistency in the model and help the model to generalize well to unseen data. So these two losses indeed form what's so-called fixed match approach, which was presented in Europe's last year. Now, our approach, or indeed, while this simple semi-supervised federated learning algorithm is quite simple, we argue that the learned knowledge for individual clients could be further improved by involving similar clients in the training. So we don't only base or dependent on the model that has been trained in supervised fashion, but maybe we could also leverage knowledge from other clients. So our approach is inspired by the peer learning concept introduced in social science literature, which utilize similar peers to help the target client in the task at hand, for example, pseudo-label generation. So our method consists of 3 steps. First, we need to find who are the peers, the similar ones. So we need to build the communities. And here we realize this by simply measuring or building the similarity matrix between the clients and measuring the similarity between the model parameters of these clients. Once we find the similar peers, for example, client 9 and client 4, similar to the client 6, then we could send these peers to this client to help him in generating the pseudo-LiPo. However, to reduce the cost, the communication cost, and avoid any privacy breach, we apply step 3, which is the model ensemble here, to generate these anonymized peer. To get more insights how this works, you remember this, in semi-supervised learning, we do have LiPo data that try to minimize the cross entropy in a supervised fashion. We do have the other part, which actually we use the unlabeled data to get the pseudo-LiPo. The main difference here that we also bring another peers, yeah, well, we pass the unlabeled data not only to the local model, but also the other peers, and then we get the predictions to generate the pseudo-LiPo. So now the pseudo-LiPo is generated by, indeed, the help of not only the local client, but also other peers. So without going into further details, we have leveraged around 38,000 skin lesion images from multiple sites and distributed them into 10 clients with different distribution as reflected here. Additionally, we test the global model on unseen client who had 33 skin lesion image from ISAC 20. And this is the results that we got. Probably better to explain what is lower and upper bound. So the lower bound, where we only train either the local or the fit average only on the small portion of the annotated data which are available. Most of these semi-supervised learning approach will be leveraging the unlabeled data available in these clients. While the upper bound model, we reveal the labels of these unlabeled data and we trained the models on these all annotated, so including the unlabeled data as annotated. And this is what we define it as upper bound model. The most interesting results here that fit average model is outperforming all local models, no matter if you leverage the label or reveal the label or not. So which suggesting that aggregating knowledge across different clients is more beneficial than exploring local label data or unlabeled data. So it's even better than SSL approach, like this fixed match approach. Now let's have a look at the results of the FidVal, our approach, where with different values of T, where T is the number of peers that we send to the target client. What you can observe here, that most of these results outperforming all the state of the art with probably a big margin. They are somehow compatible, however, at the cost of the communication. So this suggesting that probably sharing one peer is probably sufficient to have a pretty cool performance. However, this might be at the cost of the privacy. And this is where we introduce this peer anonymization, where you could still keep this performance and probably slightly better at low cost. What we also investigated next is the influence of the number of peers in building or shaping this community. So what you see here on the right-hand side is indeed the exact number of clients per database. So for example, we picked 3 data clients coming from the Hampton K database, 5 clients from the ISAC database, and so on. And what you see here on the bottom figure is indeed the similarity matrix between the clients. And they are ordered such in a way that the first 5 clients coming from the ISAC database, the second 3 clients are coming from the Hampton K, then these are individual clients. And the brighter spot in these similarity matrix means there's a high similarity and you could indeed profile these clients and know who is similar to whom. But what you could observe, when we add more peers to the learning, then more or less all the clients would become somehow similar to each other. So the take-home message from this experiment, that the number of peers that you need to send to the target client should be a function of both diversity and cardinality of the community. So finally, we also try to measure see the generalization performance on unseen clients, which was Isaac 20. And what we could see here that our model outperforming other models, even like the upper model, in detecting malignant cases, which is quite surprising to us. To sum it up, I presented 2 works on brain pathology segmentation in unsupervised fashion, and another work on skin lesion classification in a semi-supervised way. In both works, we found out that private local knowledge and experiences that collected from independent sites from that long tail distribution or distributed in different clients were quite helpful to improve the model performance. However, it requires sharing high-level meta-knowledge and proper coordination and aggregation. So this is the end of my talk. I'm also happy to share there are a couple of activities that are coming up at MICAI, including the Federated Tumor Segmentation Challenge and the second version of our Distributed and Collaborative Learning Workshop. Besides, I have also a few openings for PhD and postdoc. The deadline is today. However, if you are listening to this talk and would like to apply, then I could probably extend the deadline for a few days later. Thanks a lot, and I'll be more than happy to receive questions.